Top 10 ways we know the universe is expanding. For millennia, humans looked up at the night sky and assumed it was a fixed, eternal backdrop. Stars might twinkle, planets might wander, but the vast cosmic stage itself seemed unchanging. It wasn't until the early 20th century, with the advent of powerful telescopes and groundbreaking physics, that we stumbled upon a staggering truth. The universe isn't static at all. It's expanding. This wasn't just a minor adjustment to our cosmic picture, it was a revolution. The idea that the very fabric of space is stretching, carrying galaxies away from each other like raisins in a rising loaf of bread, forms the bedrock of modern cosmology. But how do we know the universe is expanding? It's not something you can see with the naked eye. The evidence comes from a remarkable convergence of observations, ingenious measurements, and the relentless logic of physics. Let's dive into the top 10 lines of evidence that paint a compelling picture of our dynamic, growing cosmos. 1. Galactic redshift, the universe's stretching symphony. This is the foundational observation, the smoking gun that first pointed towards cosmic expansion. In the 1910s and 20s, astronomer Vesto Slipher noticed something peculiar about the light coming from distant spiral nebulae, what we now know are other galaxies. The patterns in their light spectra were shifted towards the red end, compared to spectra measured in labs on Earth. This phenomenon is known as redshift. Think of the Doppler effect with sound. An ambulance siren sounds higher-pitched as it approaches you, blue shift, and lower-pitched as it moves away, redshift. Light behaves similarly. When a light source moves away from you, the wavelengths of its light get stretched out, making them appear redder. Slipher found that almost all distant galaxies showed this galactic redshift, implying they were moving away from us. In 1929, Edwin Hubble built on this, measuring the distances to these galaxies. He discovered a stunning relationship, now known as Hubble's law. The farther away a galaxy is, the faster it's receding from us. This wasn't random motion. It was a systematic expansion of space itself. 2. Cosmic microwave background, the echo of creation. If the universe is expanding now, it must have been smaller, denser, and hotter in the past. If you run the cosmic clock backward far enough, you reach a point of unimaginable heat and density, the Big Bang. This early, hot, dense state should have left behind an afterglow, a faint radiation filling all of space. In 1964, Arno Penzias and Robert Wilson accidentally discovered this afterglow, the cosmic microwave background radiation. It's an almost perfectly uniform bath of microwave radiation coming from every direction in the sky, with a temperature just 2.7 degrees above absolute zero. This radiation is the cooled remnant heat from the Big Bang, stretched to longer microwave wavelengths by the expansion of the universe over 13.8 billion years. The CMB's existence, its near-perfect uniformity with tiny predicted fluctuations, and its specific temperature are incredibly strong evidence for the Big Bang and the subsequent expansion. 3. Type Ia supernovae, cosmic mile markers. Hubble's law showed galaxies are moving away, but measuring cosmic distances accurately is tough. How do we confirm the expansion rate and see if it's changing over time? Enter Type Ia supernovae. These are specific kinds of stellar explosions that occur when a white dwarf star in a binary system gains too much mass and detonates. Crucially, these explosions always happen in roughly the same way and reach roughly the same peak brightness. This makes them standard candles, objects of known intrinsic luminosity. By observing how bright a Type Ia supernova appears from Earth, astronomers can calculate how far away it is. In the late 1990s, 2 independent teams used these supernovae to measure distances to very remote galaxies. They found that the distant supernovae were dimmer than expected, meaning they were farther away than predicted by a constant expansion rate. This shocking discovery showed that the universe's expansion is accelerating, driven by a mysterious force called dark energy. 4. Baryon acoustic oscillations, ripples in the cosmic pond. The early universe wasn't perfectly smooth. It was a hot soup of particles, protons, neutrons, electrons, collectively called baryons, and photons, light. Gravity pulled matter together, while the pressure of photons pushed it apart. This cosmic tug-of-war created sound waves, or pressure waves, rippling through the primordial plasma, similar to ripples spreading on a pond. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, these ripples froze in place, leaving a characteristic pattern in the distribution of matter. Specifically, there's a slightly higher probability of finding galaxies separated by a particular distance, the distance the sound waves could travel before freezing. This preferred separation distance, visible today in the large-scale clustering of galaxies, is called the baryon acoustic oscillation scale. Because this scale acts like a standard ruler imprinted on the cosmos, measuring how it appears at different distances allows astronomers to map the expansion history of the universe with incredible precision, confirming both past expansion and recent acceleration. 5. Large-scale structure. The cosmic web's growth. Galaxies aren't scattered randomly throughout the universe. They clump together in clusters and superclusters, separated by vast, nearly empty voids. This intricate network is called the large-scale structure, or the cosmic web. The way this structure has formed and evolved over billions of years provides compelling evidence for expansion. Computer simulations based on the Big Bang model, incorporating gravity, dark matter, and cosmic expansion, predict exactly the kind of web-like structure we observe. Tiny density fluctuations seen in the CMB acted as seeds. Gravity caused denser regions to attract more matter, growing into galaxies and clusters, while expanding space stretched the distances between them, creating the voids. The observed distribution, size, and evolution of clusters and voids match the predictions of an expanding universe model remarkably well. If space weren't expanding, gravity would have pulled everything together much more tightly and uniformly than we see. 6. Abundance of light elements. Big Bang's recipe book. The very early universe, the first few minutes, was hot and dense enough to act as a nuclear reactor, fusing protons and neutrons into the lightest elements: hydrogen, helium, and trace amounts of lithium. The theory describing this process is called Big Bang nucleosynthesis. The predicted abundances of these light elements depend sensitively on the conditions in the early universe, particularly the density of ordinary matter and the expansion rate. A faster expansion would leave less time for fusion, resulting in less helium and more hydrogen. By measuring the actual amounts of hydrogen, helium, and lithium in the oldest, most pristine gas clouds and stars, astronomers find an astonishingly precise match with the BBN predictions, only if the universe started in a hot, dense state and has been expanding ever since according to the rate described by Hubble's law and refined by other measurements. 7. Age of the universe versus age of oldest stars. Cosmic consistency check. The expansion rate, Hubble constant, allows us to estimate the age of the universe, how long it's been expanding. By measuring the current expansion rate and how it has changed over time, factoring in gravity and dark energy, cosmologists arrive at an age of approximately 13.8 billion years. This provides a crucial consistency check. If the universe were younger than the oldest objects within it, our model would be wrong. Astronomers can estimate the ages of the oldest star clusters, globular clusters, and the oldest individual stars by analyzing their composition and brightness. These independent measurements consistently show that the oldest stars are indeed slightly younger than the calculated age of the universe, typically around 12 to 13 billion years old. This agreement supports the expansion timeline derived from cosmological models. Finding stars significantly older than 13.8 billion years would pose a major crisis for cosmology. 8. Gravitational lensing, distorted views through expanding space. Einstein's theory of general relativity tells us that mass warps spacetime. Light rays passing near a massive object, like a galaxy cluster, will be bent, much like light passing through a lens. This phenomenon, gravitational lensing, causes background galaxies to appear distorted, magnified, or even multiplied into multiple images. The amount of lensing depends not only on the mass of the foreground object, but also on the distances between the observer, the lens, and the background source. These distances are directly affected by the expansion of the universe. Measuring the distorted shapes and positions of lensed galaxies at various distances allows cosmologists to probe the geometry of spacetime and how it has stretched over cosmic history. The observed patterns of gravitational lensing across the sky are consistent with the geometry predicted by an expanding universe containing dark matter and dark energy. Integrated Sachs-Wolf effect, CMB hotspots from stretching wells. The cosmic microwave background isn't perfectly uniform. It has tiny temperature fluctuations, about 1 part in 100,000. As CMB photons travel across billions of light-years towards us, they pass through the gravitational potential wells of large-scale structures like superclusters, which attract photons, giving them energy, and voids, which photons climb out of, losing energy. In a non-expanding, matter-dominated universe, the energy gained falling into a well would be exactly cancelled by the energy lost climbing out. But in an accelerating, expanding universe dominated by dark energy, these potential wells stretch and flatten while the photons are passing through. This means photons climbing out of a well lose slightly less energy than they gained falling in. This subtle effect, called the integrated Sachs-Wolf effect, causes CMB photons passing through large superclusters to appear slightly hotter, bluer. Detecting this correlation between CMB temperature and the location of large-scale structures provides independent evidence for cosmic acceleration. Overall consistency. The puzzle fits together. Perhaps the most powerful evidence isn't a single observation, but the remarkable consistency across all these different lines of evidence. Cosmologists have developed a standard model called Lambda CDM. It describes a universe that began with a Big Bang, is expanding and accelerating due to dark energy, represented by lambda, and contains normal matter, cold dark matter, and photons. This relatively simple model, with just a handful of key parameters, like the expansion rate, the densities of matter and dark energy, successfully explains and matches the detailed observations from galactic redshift, the CMB, Type 1a supernovae, BAO, large-scale structure, light element abundances, universe age, lensing, and the ISW effect. The fact that measurements using wildly different techniques all converge on the same basic picture of an expanding, accelerating universe described by Lambda CDM is incredibly compelling evidence that the model, and the expansion it describes, is fundamentally correct.
Conclusion: an unfolding cosmos. The picture is clear. We live in a dynamic, expanding universe. From the stretched light of distant galaxies to the faint echo of the Big Bang, from exploding stars serving as cosmic rulers to the subtle temperature shifts in ancient radiation, the evidence is overwhelming and multifaceted. While mysteries like dark energy remain, the fundamental fact of cosmic expansion rests on a century of rigorous observation and theoretical validation. Our cosmic home isn't a static stage, but an epic story still unfolding.